Today, I'm going to share with you a topic about Apple's OTA update. In this session, I will talk about how to bypass the signature verification and hijack the system kernel during the update process. First of all, let me introduce myself. I am a bug hunter who mainly focuses on Apple product security. I was previously a security researcher at Trend Micro and left the company in May of this year. So I work for myself now, and most of our time is spent doing reverse and debugging. Here are some of the bugs that I discovered over the past 3 years. As you can see from the list here, there are more than 140 CVEs, most of which are Apple vulnerabilities. Well, this is my agenda for today. First, I will talk about Apple's update methodology, especially the OTA update, what it is and how it works. Next, the following are the new vulnerabilities that I discovered during my research. I will talk about their root cause, how I exploited them, and how Apple addressed them. Finally, I will summarize the talk and make some conclusions. Well, let's go through the basics of Apple update. As far as I know, there are now 3 main ways for Apple to update macOS. The first method is completely upgrade the system. The second is the OTA update, which I will discuss in more detail today. And the third is called RSR. A full upgrade is deployed by an install assistant PKG file, which contains the install macOS assistant application. This usually happens when there is a new major version released. For example, upgrading from macOS Catalina to macOS Big Sur or macOS Monterey, and so on. Of course, users can also upgrade manually by downloading and installing the assistant application. There is a website that collects the assistant packages for almost all macOS versions. The links are below. In most cases, macOS updates are done through the OTA update. OTA is short for over-the-air. In the System Settings panel, we can update the system directly by clicking the Update button. RSR is also known as Rapid Security Response, which is new in macOS Ventura. It delivers important security improvements between software updates. For example, improvements to the Safari web browser, the WebKit framework stack, or other creative system libraries. It may also be used to mitigate some security issues more quickly, such as issues that might have been exploited or reported to exist in the wild. This is the simple comparison of the 3 upgrade methods. A full macOS upgrade is the complete installation and therefore takes more time. It is usually performed once a year, and the size of the full installer is about 14 gigabytes. An OTA update is an incremental update and is therefore faster and smaller. It is used for minor version updates, usually every 2 months. RSR is also an incremental update, is the smallest in size and is the least time-consuming method. But the frequency of RSR updates is variable and depends on urgent zero-day vulnerabilities. When Apple considers there is an urgent vulnerability in WebKit or similar that's already being actively exploited, you might receive an RSR update. The OTA update packages are downloaded from the Apple CDN server. As you can see from the table, the OTA packages are customized for the current OS versions. For example, to update to 12.6, the packages for 12.5 and 12.4 are different. The update process is to apply the patch codes. So different OS versions have different patch codes. In most cases, the older the system, the larger the package size. After downloading and unzipping the OTA package, we can see the package contents as follows. Next, Let's check the contents of some essential files. The boot directory contains something related to the boot process. The real patch code for the incremental update is located in a directory named payload v2. There is a created file named payload.bomb that lists all the items in the OTA package and their checksum values. The file payload.bomb.signature is used to verify the integrity of the payload.bomb file. The files pre.bomb and post.bomb list all the items and all their checksum values on the system before and after the update. The info playlist file provides some basic information about the current OTA package, such as the pre-version, the target version, etc. In the payload v2 folder, there are some important files to be aware of. The new data files in the new system are compressed into a file named data payload. The ECC data folder contains some files related to file permissions. The links.txt file lists all hard links for the new system. The remove.txt file lists all items that need to be removed from the current system. The general update process could be abstracted into 3 phases. The first stage is to download and extract the update brain service. The second stage is to download and extract the OTA package. The third stage is to spawn the update brain service with the OTA package. Well, let's take a look at the first stage. So, where does the system download the update brain service from? After some research, I found the download URL located in the XML file here. From this file, we can see the base URL and the relative path to build a complete URL. It contains the version, release date, package size, SHA-1 value, and other useful information. After fetching the download URL, the process NSURL session D is responsible for downloading the update brain service to a temporary location. At the same time, the streaming unzip XPC service decompresses it to the same temporary location. Next, the mobile OSD process moves the decompressed contents to the trusted location /system/library/accessv2. Finally, before the launchd process spawns the update brain service, the XPC service bundle will be copied to its staging path. The second stage is similar to the first. The differences are the XML path, the download URL, and the target location. The third stage is the update brain service itself. This particular XPC service has a number of juicy entitlements. For example, the entitlement com.apple.release.install.heritable grants itself and all its child processes permission to modify the SIP protected locations. Moreover, the entitlements com.apple.apfs.revert to snapshot and create sealed snapshot would allow the service to update the SSV protected contents after a reboot. One more thing we should note is that it is signed with the flag library validation. Therefore, we can't enjoy these entitlements directly by injecting dynamic library into this service. Through simple reverse engineering, I found that it provides a Mac service called Update Brain Service 2 with a protocol called MSU Brain Private Interface. It accepts all XPC connections from any client directly by returning yes in its delegate method. However, during my research, I realized that the protocol methods in this service are not implemented. So maybe I will check again in a future release. There is another Mac service named Update Brain Service that doesn't have a 2 in its name. It is implemented through a low-level XPC API in the C language. In the XPC handler method, we can see that it dispatches XPC requests through a global array. If the client has the required entitlement for the corresponding request, the service will call the processing routine function accordingly. The global dispatch table has 7 elements, each with 3 members: the name of the operation, the required entitlement string, and the address of the actual processing routine function. Okay, let's move on to the vulnerabilities during the OTA update process. The first one is CVE 2022-42791, which bypasses the signature verification of the OTA package and ends up with arbitrary kernel code execution. So my motivation comes from this question. Can I modify the OTA packages before applying the patches? Well, let's review the second stage of the update that we talked about earlier. First, we can confirm that the final path of the OTA package is protected by SIP. However, we will notice that the extracted content is first placed in a temporary location, which is not restricted at all. It is owned by NSURL session D and can be modified directly by the root user. Therefore, there is a time window to modify the contents before the mobile SSD process moves to the trusted location. As a result, the content of the OTA package in the trusted location is not trustworthy and needs to be verified. When I try to replace payload bomb file directly, the mobile SSD process fails to call a file API due to a permission issue and therefore refuse to move to the final path. This is because the new file is the symlink created by the root user. But the truth is that once it passes the check here, it will call the API rename to move the package content. So I replaced the target file too early. So what does the successful log look like? Fortunately, there is a keyword that indicates a time window of passing the check. So once that keyword is monitored from the log, we can replace the target file. So next, here is my second attempt. Monitor the logs and replace the target file from the OTA package as soon as the keyword moving file is detected. The tempered content was then successfully transferred to the trusted location. However, the update brain service stops preparing the OS update because it is the duty of this service to verify the contents of all trustworthy OTA package from a trusted location. So, how does it validate the OTA package? As mentioned earlier, the payload.bomb file lists all the items and their checksum values in the OTA package. First, we can dump the contents of the bomb file by using the system command lsbomb. Then, we can recalculate the new checksum value for the target file. Finally, we can use the makebomb command to generate a new bomb file based on the modified dump. Here is the function that verifies the package contents. It opens the file payload.bomb and reads its contents. Next, the function compares the file digest value specified from the payload bomb file with the true digest value on the final pass. If one of the digest values is not equal to the expected one, the function returns false and the verification fails. But how does it verify the payload.bomb file itself? Another function named verify package signature is responsible for the verification. First, it opens the bomb file and calculates its SHA-1 value. Then, it opens the payload.bomb.signature file and reads the signature file content. Next, it fetches the public key from the system certificate file, which is protected by SIP and SSV. Finally, it verifies the signature with the public key, the calculate SHA-1 value, and the signature file content by calling the API from security framework. So here is a classic time of check, time of use issue. The payload.bomb file located in the trusted location can't be modified directly, but we can replace it with the symbol link before the mobile SetD process moves the OTA package. Therefore, the payload.bomb file can be modified at any time by using the symbol link. Next, in the function verify package signature, it reads the bomb file from a controlled location according to the symbol link. So we can use the original bomb file to pass the check here. Then, in the function verify package contents, it also follows the symbol link and uses the controlled bomb file to verify all the other items in the OTA package. So at this time, we can fake the bomb file to fake all the other items in the OTA package. This was my third attempt, and it worked. First, copy the original payload bomb file to a controlled location. Then, monitor the logs and replace the bomb file with the symbol link as soon as the keyword is detected. Next, the symbol link is successfully moved to the final trusted location. Then, after passing the function verify package signature, the bomb file is forged in the controlled location. Finally, all items in the OTA package can be tampered with. Next, what can we do after bypassing the signature verification? My first exploit is a SIP bypass. The function parallel patch remove files reads the removed.txt file in the OTA package and removes all items specified in the file. As a result, I could get a primitive to remove arbitrary SIP protected paths by modifying the txt file. The exploit works on all Mac platforms, including the Intel Macs and Apple Silicon Macs. The SIP bypass primitive is not enough. I want to get more. So, can I hijack the new OS kernel? Another challenge to hijacking the OS kernel directly after bypassing SIP is the SSV protection. SSV is short for Signed System Volume. It was a new feature introduced in macOS Big Sur. In case the SIP is bypassed, it still uses an isolated read-only system volume to protect system files. Each SSV hash value is stored in the main file system metadata tree, which is itself hashed. Since each node of the tree recursively verifies the integrity of its children's hashes, the root node's hash value, called a seal, covers every byte of data in the SSV, which means that the cryptographic signature covers the entire system volume. This advanced system volume technology provides a high-level security against malware and tampering with the operating system. The basic fact is that Apple needs to update the OS kernel file via the OTA update process. Therefore, the OTA update process must have the ability to break the SSV protection. But how is this process accomplished? macOS system has a hidden update volume that is a snapshot of the current OS. All patches are then applied to that snapshot. If the update process is successful, it will update the seal value and boot the new OS. If the update fails, it will revert to the previous snapshot. After digging deeper into the update brain service, I have summarized the following key workflows in the OTA update process. As mentioned earlier, the functions verify package signature and verify package contents are used to ensure that the OTA package has not been tampered with. Once the verification is complete, a function named prepare snapshot is called to prepare the snapshot of the current operating system in the hidden update volume. Next, the function copy patched files applies the patches from the OTA package to the snapshot. And the function copy archived files extracts the payload from the OTA package into the snapshot and repairs the file permissions based on the ECC files in the OTA package. These payload files and the ECC files are in Apple Archive format. The function copy archived data files is similar to the above function. At last, the function verify post-bomb verifies the checksum values of the new system files in the snapshot. So the second exploit is to hijack the OS kernel file. My first attempt was to drop a crafted kernel file via the payload extraction functions. The steps to make a crafted data payload are as follows. First, copy the original kernel file to a writable location. Then, replace the output string of the system command uname in the duplicated kernel. Finally, use the command AA to compress the crafted kernel into an Apple Archive file, which is the crafted data payload. During the OTA update process, the crafted data payload is extracted into the snapshot as expected. However, it didn't work after a reboot. I'm not sure what the reason is. So my second attempt was to abuse the function copy patched files that applies the patches. This is the same way the OTA update process updates the kernel. The difficulty, however, is that I have to create the patch file by myself, which is in bxdiff5 format and undocumented. So I must exploit the file format first. I started with Google search for this file format and then found two GitHub repos. Both of them are used to apply a patch file to an old file and then generate a new file. However, I need to generate a patch file based on two different files, but they did help me understand the file format. From reading the source code, I know that the bxdiff patch file consists of 4 sections: header, control, diff, and extra. The header section is 88 bytes in size, with the first 8 bytes being hard-coded magic numbers. The red part is unknown and seems useless. The green parts are the hash values before and after the patch, which are used to verify that the patch was successful. The blue part is the size of the following sections. The control section is compressed using the LZMA algorithm. After decompression, the control section data is 24 bytes and consists of 3 types of command. The first is the mix length, which specifies how many bytes to mix from the diff section. The second is the copy length, and the third is the seek length. The diff section and the extra section are also LZMA compressed. After decompression, the data is a raw bytes array that is used by the control section before. My goal is to replace the output string of the command uname, so I should modify the diff section. First, using the following script to calculate the new bytes in the diff section. Then pick out the diff seek position when it reaches the input seek position. The new code in the previous slide is used to print the position. Next, rewrite the new bytes at the diff seek position. Then compress the newly created diff section by using the LZMA algorithm. Next, we can reuse the control section and the extra section directly. Finally, update the hash value and size in the new header section. After I made a patch file for the kernel, it worked as expected. Although it only works on Intel Macs without the T2 chip, I was able to inject malicious shellcode into the kernel and execute arbitrary code at ring 0. The challenge for other Mac platforms is the hardware mitigation called secure boot. The default setting is full security, which offers the highest level of security. During startup, your Mac verifies the integrity of the operating system on your startup disk to make sure it is legitimate. If the OS is unknown or can't be verified as legitimate, your Mac connects to Apple to download the updated integrity information it needs to verify the OS. This information is unique to your Mac, and it ensures that your Mac starts up from an OS that is trusted by Apple. Here is how Apple patched this vulnerability. At line 180, it calls the function digest file nofollow to calculate the SHA-1 value. Internally, it opens the payload bound file with the flag nofollow to block the symlink attack. Next, I'm going to introduce another SIP bypass vulnerability and try to exploit this issue to attack the kernel directly. As we can see from the screenshot, the extracted photo itself is restricted, but the files and the photos inside are not restricted. An example is the photo named asset data. Therefore, we can directly modify the contents of the OTA packages, even after they are moved to the final trusted location. So it is useless to verify the integrity of the OTA package. We can get a SIP bypass primitive directly by modifying the OTA package contents after it passes the package verification. Through my research, I realized that the root cause of the issue lies in the function named move target to directory in the process mobile asset D. It moves the OTA package contents by calling the API move item at URL, which itself preserves the source file flags and extended attributes. The contents on the final path are unrestricted because the source files are unrestricted. Now, Apple has addressed the issue as follows. It first used the API copy item at URL to copy the OTA package contents to the intermediate path, and then used the API move item at URL after the copy. Now, the contents on the final path will be restricted because the files written by the process mobile asset D are restricted. Well, what else can we do after bypassing SIP? As mentioned earlier, we can execute arbitrary kernel code by replacing the kernel patch files as done in Explorer 2 before. But this is a bit complicated. Can I replace the restricted kernel file itself directly from the snapshot? During my research, I realized that if I replace it too late, it won't work after a reboot. However, if I replace it too early, the new kernel will be overwritten by the patch. So what is the right time to replace the kernel file from the snapshot? How can I catch this timing? By monitoring the restore log, I found that it outputs some useful information during the patching process. When all the patches have been applied, it goes to the next stage and outputs the log, unarchiving files in parallel. So I wrote a function named spin for log to wait for the right moment when all the patches are up. Next, I can replace the original kernel with a maliciously infected one directly from the snapshot. As before, it only works on Intel Macs without the T2 chip, which don't have the secure boot mitigation. Now, let's watch the demo. sorry, I need to. Okay. First, let's check the current OS version. It is 13.3, and there is a new version 13.4 available. And the output of uname is normal. Then run the exploit OTA program and click Update Now button. Now, let's wait for the OTA update process. It will cost about 30 minutes, so the video is speeding up. Let's wait. It is now applying the patches from the OTA package content. Okay, 100%, and the keyword on archiving files in parallel is detected. So it is the right time to replace the kernel and the kernel cache. My exploited program finished its job. Let's wait for the reboot. Rebooting. After the reboot, we will check the current OS version. As we can see, it is 13.4 now, so the update process is successful. However, the output string of system command uname have been checked by Mickey Jin. Okay. Let's come back to my slides. And there is one more issue that I discovered during this research. Apple didn't assign a new CVE for this. They just credited me in the additional recognition. Now we know that it is the duty of the update brain service to verify the contents of untrusted OTA package. The verification depends on the file payload.bomb. However, I found that not all files in the OTA package are listed in the bomb file. For example, the RAM disk folder, the boot folder, and so on. This leaves many critical files unprotected, so there are many ways to exploit the issue. First, removing and touching the RAM disk DMG file will lead to a DOS issue. Second, hijacking the firmware by modifying the contents of the firmware folder. Third, modifying the boot-based EFI file to hijack the boot process from the first instruction and inject the earliest shellcode to the system. The boot-based EFI file is in Windows PE format. I didn't develop my own EFI program to change the OS boot process. For a quick proof of concept, I just patched the entry point code to EBFE, which is a short jump instruction for a dead loop. After replacing the boot-based EFI file and rebooting, the system hangs into a dead loop. To verify this, I set up a remote GDB stub and connected to it remotely in AdaPro. As a result, you can see that my shell code does execute in the EFI shell as expected. In order to verify the integrity of the OTA package effectively, it is necessary to list all items in the OTA package from the payload BOM file. Now, Apple did do it after this report. Next, I discovered a new bypass through a downgrade attack. Apple has assigned CVE 2023-35983 to this report. The main executable of the update brain service is an empty caller. All functions are implemented in a dylib. Of course, the new patch code is also included in the dylib. Therefore, an attacker can perform the downgrade attack by replacing with the older version of dylib, which is signed by Apple and OK with the library validation. Similar to the OTA update package, the update brain service package can be modified from the root user. As a result, an attacker could replace update brain service with an older version before moving it to the trusted location and then exploit the older issues again. Now, Apple has refactored the whole process. It ensures that the entire process is trusted and that the package contents are not tampered with. First, the process NSURL session D creates a restricted directory called download.dir, and then downloads the update brain service package to the trusted location. Then, the newly introduced streaming unzip XPC service performs the decompression in parallel at the trusted location. Once the download and unzip operations are complete, the process later are similar. Note that both the NSURL process and the streaming unzip XPC service have the new special rootless entitlement to modify the restricted content directory. By the way, the download of OTA package also follows this new process. Okay, let's do a quick summary. In this session, I talked about what Apple's OTA update is and how it works. I also shared the vulnerabilities during the update process and how I exploited them. The POC codes are publicly available for research purpose only. In addition, I discussed how to execute arbitrary kernel code after bypassing the SIP. The OTA update process is super privileged, has the power to update SSV-protected system files. The vulnerabilities I talked about today are very dangerous for Intel Macs without the T2 chip. Secure boot is a great hardware mitigation against such attacks. Thank you, that's all. Apologize for my bad English. If you have any questions, you can talk to me later.